Morning and welcome to this lecture of mixed signal IC design. So today we'll start with unit 4, which deals with the different data digital to analog converter architectures, right? So um, in the previous unit or in the previous class we were discussing about some of the important specifications of DAC. We haven't discussed about ADC specifications yet, but we started with DAC specifications where we discussed about some of the important static and dynamic specifications, right? So today we will start doing some of the important architectures of digital to analog converters. So let me start with introduction to this. Alright, so even from the previous discussion, we know that a digital to analog converter produces an analog output. Right, 1 second. Yeah. So we know that a DAC produces an analog output, right? So DAC converts a digital data into analog. So this produces an analog output. And most of the time this analog output, not most of the time, the analog output is always proportional to the digital input. So I would say I'll write that is proportional to digital input. Now if I want to write the I'm just using the notations as A and D just to differentiate. The analog output of a DAC can be written equal to, or can be written as a constant alpha into D. D is the digital input data, just a form of representation, right? But we know that for a digital quantity, generally for this or this one is basically a dimensionless quantity, right? So what we have on the left is analog and what we have on the right is digital, and D is a dimensionless quantity. So now the constant alpha, or the value, the alpha is the one who actually sets the dimension of this, actually sets the dimension of A basically, right? So in the discussion of the specifications of DAC, how we wrote is, we wrote that the analog output V out is generated from a reference voltage, and we also wrote that it is Vref into the digital data divided by 2 to the power of n. This is how we express the analog output data here. So this is analog, and what we have here is digital. This is analog and this is digital. And generally to normalize the digital data with respect to its full scale range, we are actually writing this factor here, d by 2 to the power of n. This is how one way of representing it. This is true when this alpha, so when I will say when alpha is a voltage quantity, we can write in this form: V out. V out, generally we express in terms of voltage only. The output is expressed in terms of voltage. If alpha is a voltage quantity, we can express that alpha as Vref into d by 2 to the power of n, where we will have the dimensions of a voltage, right? Now it is not mandatory that always this alpha quantity should be voltage. It can be current quantity as well, right? So now for that, if alpha is a current quantity, I can write analog output A as the current. In place of a reference voltage, then we will have a reference current. So A can be written as Iref into the digital data D, right? Now the way we implement for voltage quantities and current quantities will be slightly different. We will look at various architectures which will include all these kind of things. All right. So in short, what I want to introduce about architectures is, we know that the data, the input is digital and the output is analog, and always output will be produced as produced in terms of a reference voltage, or with respect to a reference current, and this is how we generally express that. Right. Now from yesterday's discussion, especially when we are discussing about DNL and INL, right? Those two are some of the two important specifications of a DAC, which talks more about the linearity of the data converter, right? So if you remember, in case of DNL, we are particularly looking at the step height for every input digital code change. What is a step height? And step height should be ideal in the sense we are expecting equal increment, right? Now this DNL and INL are usually determined by the accuracy how we generate this output voltage from this reference voltage, or output current, output quantity from the reference voltage. It can be a reference voltage, it can be a reference current, or even it can be from charge, right? So now what I'm trying to say here is Shreyas, yeah, definitely. We generally, when it is a voltage quantity, we try to express this as different levels, right? So when I say d by 2 to the power of n, we are actually ranging or dividing the entire range of output voltage into different levels, and we are actually giving it. Generally, we will not express current in that form. We will see how we express current by taking one specific example of that. All right. Yeah, so what I'm trying to say here is the important specifications of this DAC, both DNL and INL. We know that this is a measure of non-linearity, and these two are usually determined by the accuracy, or this depends mostly on the accuracy by which we generate the output voltage, right? So the accuracy of how we generate the reference voltage, it can be in terms of reference multiplication. From a reference voltage we will multiply and we will get the output voltage, or it can be from a reference voltage we will divide and do it. So both types of things we will do. So accuracy of how we generate the output voltage, either it is through a reference multiplication or reference division, right? So the underlying point here is if a digital to analog converter wants to convert a digital data into analog, it requires a reference. That reference can be some electrical quantity. It could be a voltage, it could be a current, or it could be in form of charge, right? So if we broadly look at the ways we can do this reference multiplication or reference division, reference multiplication or division, primarily we can look at three electrical quantities. One is voltage. From a reference voltage we can divide or multiply and get it, or it can be a reference current, or it can be from charge, right? So these three electrical quantities are either multiplied or divided to get the corresponding analog voltage, right? Now yeah, so say for example, if we have a reference voltage, if the electrical quantity is voltage, generally one very common form of one common architecture what we use is called as resistor ladder DAC. We will look at the details of all these architectures. I'm just listing out which are the what are the classifications what we have. Now if the electrical quantity what we depend to generate the output voltage is, if it is a current, we use current steering circuits, and if we rely on charge, or if we use charge to determine the output quantity, we take the help of switched capacitor circuits, right? So this discussion is giving the idea that for a digital to analog converter, it is not mandatory that always you should have a reference voltage. It can be the output quantity can be generated from a voltage quantity or a current or from charge, and correspondingly we will use different types of architecture. For voltage we use resistor ladders, for current we use current steering circuits, and for charge we use switched capacitor circuits. Alright, so now I'll quickly brief about how we implement all these three types, and later we will go into each architecture in detail. All right. So let me start with this first. First one is voltage division. Voltage division, and that is by using a resistor ladder. Resistor ladder network. We will not go to the details of the architecture right now. We will actually look at the details, and we'll even go up to the nonlinearity calculations of DNL INL. But before that, I'll just give a brief introduction about these three methods. Yeah, the first thing is this voltage division by using a resistor ladder network. I think this is a very common, or this is a very basic form of digital to analog converter representation. So what we do is we'll take a reference voltage. Say we'll have a reference voltage here, Vref, and from this reference voltage or this reference voltage is divided into different segments, different equal segments, and in order to create equal segments we use resistive ladder. We use simple resistor in the form of a ladder, right? So say for example, if I want to have a n bit DAC, right? So what I do is I'll take a reference voltage and I'll divide the reference voltage into n equal segments, and for that I'll use a ladder which again composed of n identical resistors, right? So in general, how I can represent this is, in general what I can do is I'll use resistors. Let me just mark the resistors as R1, R2 up to Rn minus 1, and this can be called as Rn. So we have n equal value resistors, right? And we, from the reference voltage, with the help of this n equal value resistors, we are generating n equal segments, right? So when I say by n equal segments, here we have reference voltage V1, here we have V2, then here we have, at this point we have Vn minus 1, right? This is how we generate. All right. So now the question is, see, for example, we have an n bit DAC. So how many resistors are required for an n bit DAC? Can I get some response? Are you guys with me? For a m bit DAC, how many resistors are required? See, the requirement is we have a reference voltage. We want to generate, right? We want to generate the analog, the output quantity from the reference voltage. So we divide the entire reference voltage into n equal segments, and for that we need to use equal value resistors, right? So equal value resistors I need to use. So say for example, if I want to design a 3-bit DAC, right? For 3-bit DAC, how many resistors are required? Can I get some response from the, are you guys there? M minus 1, okay. For a 3-bit DAC, yes, 8 resistors. All right, yeah. So for a m bit DAC, we need 2 to the power of m resistors, right? For a 2-bit DAC, we need 4 resistors basically. We'll come back. We'll come back to the architecture. Yeah. So the point here is, what I'm trying to say is, from a reference voltage we can generate it, and this is how in resistor ladder network we do. We use equal value resistors to create different segments of voltages, and with that we'll convert into this one, right? So now whenever we use a resistor ladder network in the form of voltage division, the problem here is, see, for an m bit DAC we need 2 to the power of m resistors. So if we go for higher resolution, right, for a higher resolution, the number of resistors will exponentially grow, right? So the drawback of this is, this shows an exponential growth in the number of resistors, number of R what we use as a function of resolution. Right, if we go for higher bits DAC, then the resistor values also will increase in an exponential way, because it is 2 to the power of m. Now, what do you think? Now, what can be a possible DNL INL effect? How differential nonlinearity and integral nonlinearity will appear in a resistor ladder network? What do you think? What can be one possible reason for DNL or INL in a reference resistor ladder network? We know that it basically depends on the ability of the DAC to generate the equal output increments. Yeah, it primarily depends on the resistor tolerance, right, or the resistor mismatches, because we look for 2 to the power of m identical resistors, and getting those many number of identical resistors is definitely a challenge, because resistor will have its own tolerance. There will be definitely mismatches even though we integrate it on a substrate. So in this type of architecture, the main reason for DNL and INL arise from the resistor mismatches, right? We'll definitely go to the details of this resistor string or resistor ladder network. This is just an introduction I'm telling. Alright, this is how generally we go for voltage division. Now, if we look for the other way, that is through current division, the current division method. Yeah. So in current division, in the similar way, how in a voltage division what we have done is the reference voltage is divided into n equal segments. In a similar way, in a current division method, what we do is a reference current, we name it as IREF. This reference current is divided into n equal currents. It is not mandatory that we have to always go for n equal currents. We will discuss more about that. But in general, we can say that a reference current will be divided into n equal currents. Again, using if the currents are equal, generally we use n identical, I can write transistors, or basically we use certain switches as well, right? So a reference current is divided into n equal currents using n identical transistors. This is the in general how we can talk about current division. What we generally do is, say for example, if I am translating this statement into a circuit diagram, we have a reference current, and this reference current is divided into n equal currents, right? So how can I do that? I'll use set of transistors here, and this I'll use to divide this reference current into n equal currents or whatever it is, right? So this is reference current, this need to be biased, and here we'll have, say this is I1, this is I2 current, this is I3, and up to this is IN, right? This is one form of applying current division in a DAC, and here what we have seen is this is actually a uniform current division, right? Uniform current division. See, one thing what I want to say is you will get the clarity how we do this conversion only by looking at the complete architecture of a DAC, right? Because we need to see how we are applying the digital input data and how that digital input data is controlling controlling in this case, how it is controlling and how it is channelizing this currents to form the respective output quantities, right? So this is how uniform current division can be done. Other way of doing is, say for example, there is another way of doing this is called as binary current division, right? So in binary current division, let me just look at a 3-bit example. So in a 3-bit binary current division, how we can do is, there are various forms of this current division as well. So we'll have a reference current. Now in the form of binary current division, here we'll have I using a single transistor, then we use this is for generating 2I, this is for generating 4I. So instead of having a uniform current division, the other form of representing this or the other form is actually go with a binary current division, right? This is just a typical example of this binary current division. So here also we can see that again for an m-bit DAC, in this case, right, for an m-bit DAC, again how many transistors are required? In the previous case, we were using 2 to the power of m 2 to the power of m resistors, right? But in this case, how many transistors are required? Any response? Yeah, we need 2 to the power of m transistors in this case, right? So this is how we generally go for current division, right? So now when all the current sources are equal, so here you can see two representations, right? So one is a uniform current division and another one is a binary form of current division. Now, yeah, I think you will get more clarity on this, then how many number of resistors and transistors required when we go to the actual architecture, because I think that will give you a little more idea how this works, right? So now when all the current sources are equal, they are generally controlled. When we have this current division, these currents should be channelized by having a control, and that control is basically coming from the digital input data, right? So what we do for uniform, one second, I'll show that as well. Yeah, so when we have all current sources equal, generally that is controlled with the help of something called as the digital input data will be in the form of thermometer code. We'll see what a thermometer code is. So say for example, alright, so we'll do one thing, we'll come back to this current division after discussing one voltage division examples, right? So in current division, this is what it happens. We'll have a reference current that will be divided, and there are different ways of actually generating this. It can be from equal currents, or it can be with the help of binary current division, and some other forms are also there. Generally we call this as, this form we call it as segmented current steering DAC. This category we call it as segmented current steering DAC, and whenever we have binary current division, we call it as binary current steering DAC. Right. So we'll definitely come to the details of this after looking at the very basic architecture based on voltage division, right? So before going to that, for the DAC, the very important thing is the digital input data, right? And it is also important that it is not always mandatory that we have to present the input digital data only in the form of binary code. There are various other forms available which are easy to have different type of circuits. So let me first look at the digital input code or the form of representation which is available to control the DAC, or to present the input to the DAC. Right. So, as I mentioned, it is not mandatory always binary is required. There are different forms we can use. One is binary, another one is BCD form, another important form which certain DACs rely is called as thermometer code. Then there are other form representation, gray code. Then we have sign magnitude. We have 2's complement. These are the various forms, right? How we can represent a digital signal. So these are the various forms. Now, generally, there are architectures which follow one of these always, but in general, if you look at the common forms of representation of the digital input data, I'll just write decimal for reference, and then we express in terms of binary, we express in terms of thermometer. Say for example, I am looking for the decimal data for 0, 1, 2, 3. That is for 2-bit representation. In binary it is 2-bit representation. How we will represent this? We will use 0, 0, 0, 1, 1, 0 and 1, 1. This is how we represent binary, right? For 0, 1, 2, 3, for 2-bit representation. The same thing if we want to represent in thermometer code, how it is? For 0, we represent it as all 0. For 1, the LSB position, or we'll use 1, a single 1, and when it is 2, we'll use these 2 as 1, 1, and for 3 it will be 0, 1, 1, 1. This is how we represent thermometer code, where as the decimal value changes, we'll actually add strings of ones. It relies on the addition of the strings of ones in the code, right? In our discussion, we will be using based on thermometer code and based on binary. Apart from this, based on gray, based on 2's complement, based on 1 of n, like there are various other forms which we represent the digital input code, right? But these are very common. The binary and thermometer are very commonly used. Are you guys with me? Can I get some response? All right, so now let's look at the very first type, which is called as a resistor ladder DAC or a resistor string DAC. So as we saw in the voltage division, reference voltage division, what we do here is this resistor string DAC, basically this comprised of a resistor string of, will have a resistor string of, as we discussed, 2 to the power of n identical resistors. Along with resistors, we need switches as well. For all the to implement the control, we require switches. Right. Now, the analog output, what we get from this DAC, analog output, which we represent as V out, is basically coming from the voltage division, right? So is through voltage division. As we have seen, we'll use a string of resistors, and we'll tap the output voltage from the corresponding resistor, right? Is through voltage division, I can say, of the resistors at the selected switch or the selected tap, right? So if you look at a very simple resistor string DAC, say we'll look for a 3-bit resistor string DAC. what we do is, how many resistors we need? We need 2 to the power of 3, so we need 8 resistors, and those resistors are connected from a reference voltage. So 1, 2, 3, 4, 5, 6, 7, and 8. Alright, so there is a reference voltage and we connected the string of resistors, and let me just number the resistors as say R1, R2, R3, R4, 5, 6, 7 and 8, 2 to the power of 3, 8 resistors. Now what we are trying to do here is, so 3-bit means we will have 8 combinations, right? If the control is present in the form of a binary switch, it will be like there are 8 different levels, definitely we know, for a 3-bit DAC. In a very simple form, what we can do is we can tap the output from every, let me even add a switch here. This is how we connect, and all these switches can be connected together, because we know that at a time only one switch will be on, right, depending on how we present the digital input data. So maybe we need to use a decoder or some other form, because to convert, if it is for a 3-bit DAC, I need 3 to 8 decoder in order to operate this switch. So I can say this is switch S0, S1, S2, S3, S4, S5, S6 and S7, and this node voltages also we can represent as say V0, V1, V2, V3, V4, V5, V6 and V7, right. So now here from this point we tap the output, Vout will be connected to this. Now as I mentioned, for a 3-bit DAC, we might if this is a simple form of resistor string DAC, so we need to actually use a 3 to 8 decoder, which can actually control all these switches. Now how this works basically, so when it is when S0 is 1, your output will be connected to 0, right? When your S0 is 1, the output will be connected to 0. Similarly, for every switch control, we will be tapping the output from the corresponding node of the resistor, right. This is how this generally works, and it is a very simple form. Now one thing what we can comment about this architecture is, generally this architecture will result in good accuracy, provided the resistors are matched, right. The resistors are matched. Maybe we can mention that good accuracy based on a condition. And another thing is, there is no question about non-monotonicity, right? Because when we discussed about the specifications, we wrote that in certain times DNL will show the DNL value can be -1 LSB, which says that the DAC is non-monotonic. That means for some digital input there is no change in the output. When there is no change in the output, the actual increment height will be 0. And the ideal increment height is always 1 LSB. That is how we get a DNL of -1 LSB, right. So there is no question of DNL arising out of this, because we are directly tapping from the resistors, and the resistor string is available for every switch. Whenever the switch turns on, that will be connected to the corresponding resistor, and we will be getting the output directly. So we can say that output is always guaranteed to be monotonic. Always guaranteed to be monotonic, right. So these can be regarded as the advantages. At the same time, we know, like practically getting these many number of resistors with proper matching is difficult. So that will definitely give rise to some form of non-linear DNL or INL. Moreover, we can also see that the output of this DAC is connected to how many switches are there for an n-bit DAC? 1, 2, 3, 4, 5, 6, 7. Yeah, we have altogether 8 switches, right? So say for example, switch S1 is when S1 is on. When S1 is on, the output is tied to at that point output is tied to S1, where S1 represents an on switch. That is again a transistor, right? We will be realizing all this with the help of transistors. Now output is connected to an on switch. At the same time, output is also connected to the other 7 off switches. Are you getting the point? When S1 is on, output is connected to one on switch, and at the same time output is connected to 7 other off switches as well, right? So when I say the output is connected to these many number of switches, the parasitic capacitors at these nodes also matters, right? Because it's connected to switches, all these nodes will have some parasitics. So for lower resolution it might not be a problem, but when we go for large resolution, even a large parasitic capacitance will appear at the output node. So as a result of that, the speed of the conversion, because the output node should charge to that value, and that is actually driven by a lot of parasitic load there. So the conversion speed may get slower. This can result in slower conversion speed, as the output is tied to these many number of transistors at every point of time. Slower conversion speed, right? So we are discussing about resistor string DAC, but this is not a widely used DAC, at least for IC applications. But in general, for simple conversion and all, we can still use this. But if you want to solve the problem of this slower conversion speed for larger resolution, one simple solution of this is actually to go for instead of having a switch with the switch driven, instead of having the control with the help of all these switches from 3 to 8 decoder, we can actually try for a binary switch array, right? So that is a modification of this DAC. So this is an alternative. Primarily this is to reduce the parasitic capacitive load which is coming at the output of the DAC. So we go for a binary switch array based resistor string DAC. So simply when we say resistor string DAC, it is we use these many number of resistors and tap directly with the help of this decoder. The other way is we can here what we can do is we have the reference voltage. And this is 8, right? So this is R1, R2, R3, R4, 5, 6, 7 and 8. So instead of connecting all the switches and directly connecting that to the output, in a binary switch array what we do is we ensure that the control is done in the form of a binary switch. For that we have the switches in the same position. We have switches. What we do is we combine these two switches, these two, sorry, we combine these two here these two switches, these two and these two. Now from here again we'll use another set of switches, and we combine these two and these two together, and from here again we use two switches, and then we will combine this, and this is connected to V out. Right. So now what is the advantage of this? Here this is a binary switch array, so you can see that the control is in this form, right? So where this string or this series of switches will be controlled by the LSB bit, and this will be by the MSB bit, right? So since it is a 3-bit DAC, generally we write the control in the LSB we denote as D0, this as D1 and this as D2, right? So how we can do here is this will be D0 and this will be D0 bar. That form we can, that way we can control. This is D0 bar, D0, D0 bar, and this is D1, D1 bar, and this is D2 and this is D2 bar. So this is the alternative of the normal resistor string DAC by using a binary switch array. Yes. Delay in terms of propagation, it is the propagation delay in the sense, the closing of switch, right? Because the binary inputs will be controlling the switches and the switches will be closed. Say for example, look at this, it can be, say for example, if your input code is D, if you are D2, D1, D0, if this is 0, 0, 1, what will be the path? D2, 0, so D2 bar will be 1, so this will be on, this will be on. Then D1 is 0, so D1 bar will be high, so this will be on, and D0 is 1, so this is the point, right? So whenever this input data is presented, these three switches will turn on. When these three switches turn on, the output will be directly tied to this node and we will get the output voltage. Now why we basically went for this is, for the previous problem what we mentioned is, at the same time output is connected to all the switches, 2 to the power of n switches. If n bit means all 2 to the power of n switches will be connected to the output, and all the parasitic load will come, which is actually affecting the conversion speed, right? But now you see, since your D2 is 0, this will be open, so the output is connected only to this this path, right? So the binary switch are connected to at most n switches, right? If it is a 3-bit DAC, and at most n switches that are on, right, and n switches that are off, thereby the conversion speed is increased. Now talking about the latency, talking about the delay, definitely the delay will be there, but you are thinking, I think you are thinking the other way, no? Previously when the switch is directly disconnected, but that is having a disadvantage, right? Instead of driving a huge load there, that has actually comparatively reduced, right? But at the similar at the same time, you will also see that if you want for large large resolution or high bit resolution, we might need a large chip area, because we need to include those many number of switches and resistors. Now resistors can be definitely made small to minimize the chip area, but again we'll have the issue of power dissipation, right? Because let me make those points here. I'm just writing it as disadvantages. One is large chip area for higher resolution. Right. Now to reduce chip area, we can actually go for, there are different forms of having resistors on a substrate, right, in an IC form. There are different way we can minimize the chip area by making R small, but even then the power dissipation would be a critical issue, because current will be flowing through all these resistors at all times, right. The reference voltage is, the current is flowing, and the reference the voltage is available at all the resistor nodes. The only thing is the switch is controlling, and switch is controlled depending on the digital input data, and we are getting output only at that specific instant, but the resistors are carrying current all the time, and for that reason the critical issue can be power dissipation. Alright, but nevertheless, this is one of the most simple and common DAC architecture which is available. We'll go to the details of this. We'll see little more details in the next class. So if you have any questions, you can ask now.